Example 8, find the relative extrema for f of x equaling, we have a fifth degree polynomial equation, and you're going to see that the second derivative test is much faster on polynomial equations to find relative extrema because you don't have to worry about a sign chart, you don't have to worry about making intervals, you just find your critical numbers and plug them into the second derivative. Okay, so let's do that. So f prime of x is equal to, leapfrog that down, negative 15x to the fourth, leapfrog the 3 down, plus 15x squared. Okay, we need our critical number, so we got to set this thing equal to 0 and maybe do a little bit of factoring. Let's factor out, let's say, a negative 15x squared, and then I would have x squared minus 1, right? Okay, and then let's set this thing equal to 0. Oh, I already have. Where is this thing equal to 0? So it's equal to 0 at 0 and then also at plus or minus 1. So let me ask you a question. What could possibly happen at these two places? These could be potential mins and maxes. So these are critical numbers, and those are potential min-max. Now, if I were using the first derivative test, I would make intervals. I'd break up the domain of this using these critical numbers and then make a little sign chart and stuff. Okay, but I won't have to do that if I'm using the second derivative test. I'm just going to check the concavity at each one of these points. So second derivative, let's go back to this non-factored form right here. So leapfrog that power down. It's a negative 60x to the third, and then plus 15x. Nope. Plus 30x. And we do not need to see where this is equal to 0. Where it was equal to 0 would be possible points of inflection, but that's not what we're doing here. But I would suggest factoring it because it's a little bit easier to plug numbers in whenever it's in factored form. So I can factor out, let's say, a negative 30x. Then inside here would be a 2x squared minus 1? Minus 1. Okay. And this is our second derivative. We're going to plug our first derivative points in there, our critical numbers in there, and see if it's positive or negative. So here's the first one, 0. So if I plug 0 in here, I really don't have much work to do because this one right here is equal to 0. Doesn't matter what that one is. It's equal to 0. What does that mean? The first derivative is equal to 0. The second derivative is equal to 0. I know nothing. Question mark? It's still a possible minimum or maximum, but the second derivative test fails. So second derivative, how do you spell that word? There we go. Test fails. It has to be, the second derivative has to be either positive or negative, not 0. So what do you do then? In this case, you have to go back to the first derivative test. And we'll do that at the end. So I'm being totally lazy. I'm going to get through the second derivative part of this because that part is easier for the other two. We've got to plug in a positive 1 and a negative 1. So let's plug in minus 1 here. If I plug in minus 1, again, I just need the sign of this thing. So negative times this negative is going to make this positive. And inside here, this is going to be a negative 1, which is squared. Let me positive times 2, that's bigger than 1, that's also positive. And we get a positive number. This is greater than 0. So it's concave up here. So maybe you just draw yourself a little picture, maybe a little bit easier for you to remember. Got concave up, got a horizontal tangent line. This must be a relative minimum. How do I justify this? On the calculus exam, I'm going to say f of x has a relative minimum at x is equal to, what was that, -1 that I stuck in there? Because, and I need to say two things, f prime of -1 is equal to 0, and f double prime of -1 is positive. And that would be sufficient justification. You don't have to use the words second derivative test. As a matter of fact, you don't want to, because you have to point out you got a critical number and the second derivative is positive. All right, let's do the same thing one more time to the positive one. So f double prime of 1 is equal to, where's this? So we're going to have a negative number outside here. This time, this is still going to be positive. Negative times positive. Negative times positive. This time is less than 0. This time it's concave down. Again, draw yourself a little picture. Concave down, horizontal tangent line. This one is a relative maximum. Okay, and a justification. It's going to be very similar to what I wrote up here. We're going to say that f has a relative maximum at +1 because the first derivative is equal to 0 there, and the second derivative is negative. All right, now remember, second derivative test failed at 0. So what do you have to do? You have to test, go back to the first derivative test, and check to see on either side what the heck is happening. So you have to set up intervals around 0. First, here I go again, not being able to spell the word derivative as a calculus teacher. Test. And we don't have to check all of them. That'd be insane. We just have to check the ones around 0. Intervals. Because if we had to check all of them, why didn't we just do the first derivative test all along? We're going to check from -1 to 0 and from 0 to +1. We need some test values to plug in here. And how about plus or minus a half? Plus or minus a half. Okay, first derivative test. We plug these test values into the first derivative in order to be able to tell something about f of x. So what was the first derivative? Heck if I know. It's way the heck up here. We want to plug this into our factored form. Okay, when I plug in a -1/2, I square it, it's positive, times this negative, it's negative on the outside. If I stick in a -1/2 here, square it, it's a positive number. It's a fourth though. Fourth minus 1 is going to make this a negative. Negative times negative makes this positive. So this one is plus, meaning that f of x is increasing. Not concave up, but increasing. Right? If I were to stick in a positive 1/2, so I stick in a positive 1/2 here, it's positive times this negative number, this is negative on the outside, and 1/2 squared is positive 1/4. It's the same thing that it was before, still a negative. Negative times negative is a positive. And we do not change from increasing to decreasing. The first derivative does not change signs. Therefore, you have neither a minimum or a maximum at x is equal to 0. All right, so now, of course, you're looking at this and going, why did I do the second derivative test if I had to revert back to the first derivative test in order to test 0? Well, you don't always know that's the case. Let's say you luck out. If you lucked out, look how much faster and easier that second derivative test definitely was whenever you have a polynomial function. That's not always going to be the case. You are going to see in the coming lessons that there are instances where the first derivative test is absolutely impossible to apply, and the best that we can hope for is the second derivative test. And that usually happens when we have derivatives that are in terms of both x's and y's, so one that is defined implicitly. And the other case is that I might just have a graph of the second derivative, and I know what the critical numbers are, and then I'm basing my judgment on the graph using the second derivative test. So let's take a look at what the graph looks like for this particular one. And the second, well, did I not have a picture of the second derivative? No, I don't. But I can confirm, in fact, that we have a relative minimum here at -1, relative maximum here at +1. And look what actually did happen at 0. We had a point of inflection.